All right, guys, this is a little video on thermochemical equations. And thermochemical equations are just, they're basically just balanced chemical equations that you're familiar with here. So this is the synthesis reaction that forms hydrochloric acid from our reactants here, hydrogen gas and chlorine gas. But along with the chemical reaction balanced like this, we also have an amount of energy. And so I'm going to put this number here. Okay, so this is a reaction that actually produces energy. It produces 185 kilojoules of energy as per this balanced equation. So as long as you have 1 mole of hydrogen, 1 mole of chlorine, they're going to react and theoretically make 2 moles of hydrochloric acid and produce 185 kilojoules of energy. So this is what a thermochemical equation looks like. It just includes an amount of energy, okay? Now, you'll notice where that energy is written in here. If the energy is written into the equation as a product, then the reaction is exothermic, meaning that, you know, the reaction actually produces energy, and energy is not a substance necessarily, but you got to think of it as sort of being produced in the reaction. Okay, now here's another example of a thermochemical equation. This is just a balanced equation at this point. I'm going to put this number in. Okay, 182 kilojoules. And so this is an endothermic reaction, and you'll notice that the energy is now on the reactant side of the equation, and that just means that along with the actual reactant of mercury oxide, we're going to need a quantity of energy to make this reaction take place. So energy is required. It's on the reactant side, and when it's written on the reactant side like that, then you can consider the reaction to be endothermic, okay? And then there's another way you're going to see chemical equations written from time to time, and that looks like this. Here's the same two equations, and you'll notice that instead of the energy being written into the equation as either a product or a reactant, it's just sort of after the equation is written, you say delta H equals, and then this negative 185, that's like saying the 185 here. Now, there's no such thing as negative energy. This symbol here, the positive and negative symbols of those delta H numbers, that tells you whether the reaction is endothermic or exothermic. So if you're given a thermochemical equation and the delta H is listed as a positive number, consider that to be endothermic, and if it's a negative number, consider that to be exothermic. And here's just why that's the case. So it's not that an endothermic reaction produces negative amounts of energy. It's just that the energy flow, where the energy goes, is in the downward direction from high to low, sort of in the negative direction. Okay, and then in an exothermic reaction, we have energy increasing in this sort of positive direction. Okay, so just think of it that way. A lot of kids get confused and they think that this is a negative amount of energy, but it's not. It's just the symbol that shows whether it's endothermic or exothermic. Okay, all righty. So we can use thermochemical equations to do some stoichiometry work. And when we do stoichiometry and thermochemical equations, you have to remember that the delta H is directly proportional to the amount of reactants and products in the reaction. Okay, so consider this reaction. This is an exothermic reaction because the energy value here is written in as a product. This is iron oxide reacting with aluminum to make iron and aluminum oxide along with a bunch of energy. This is a really cool reaction. This is thermite, actually. And of course, the other way you'd see it would be like this, where the delta H is listed as a negative number here. And so what these numbers mean, they're kind of this is the balanced equation for the reaction, and that just tells you that if 1 mole of iron oxide reacts with 2 moles of aluminum, and those are referring to the numbers that are the coefficient values here in front of our reactants. So 1 mole of iron oxide, 2 moles of aluminum, that should get you not only the 2 moles of iron and the 1 mole of aluminum oxide, but it should also release 850 kilojoules, okay? So that 850 is specific to these numbers, okay? So if you change those numbers, then you're gonna change the amount of energy, just like you'll change the amount of product that gets produced as well. And so if you double the amount of your reactants, you should get double the amount of energy. And if you cut the reactants in half, you should be able to get just half of the energy out of the reaction. So that's how that works. And that leads us into doing a few different types of stoichiometry problems. Let's do a few of those guys. So here's our first problem we'll do. And we're just going to work within the realm of moles here. So we'll work with our same iron oxide and aluminum reaction. So if 3.5 moles of aluminum react with excess iron oxide, how much energy is released? And so what you know is that if 2 moles were to react with excess iron oxide, then 850 kilojoules would be released. But we don't work with 2 moles of aluminum, we're working with 3.5. So here's the setup that you use. It's a little dimensional analysis cross. So we're going to take the moles of chemical A, and remember that chemical A is the chemical in the problem that you have an amount of. So we have an amount, 3.5 moles, of aluminum. So aluminum is chemical A. So we're going to put the amount that's given to us right here in this upper left-hand part of this dimensional analysis. Over here, this is like the mole to energy ratio. Okay, so the coefficient of chemical A we've defined as aluminum. We're going to use that 2 right there in that spot. And then this is the absolute value of the delta H. And so instead of using a negative 850 there, we're going to just use 850. And here's those numbers scratched into place. Again, the 3.5 is this. The 2 comes from the aluminum's coefficient. That's that number. And then the 850 comes from the delta H. Okay? And so we can go ahead and solve that, I suppose. Let's figure this out. So 3.5 times 850 divided by 2. So we should get 1487.5 kilojoules of energy. Okay, that's how much energy would come out of having 3.5 moles of this aluminum and excess iron oxide. Okay, let's do one more practice problem, and here's this is an endothermic reaction, and we know that because our delta H is given to us as a positive number here. So this is the synthesis reaction of nitrous oxide from nitrogen gas and oxygen gas. So let's just consider that 12.5 moles of nitrogen monoxide are produced. How much energy is required? So again, with stoichiometry, you know, you're going to have an amount of something, and then you're asking a question about energy. So in this case, we don't have an amount of a reactant, we have an amount of product, right? But we still follow the same guidelines, okay? So the 12.5 moles, that's the number that goes here. The 2 comes from the coefficient of the chemical in the question, which is nitrogen monoxide. And then the 181 is that number right there, okay? So let's figure this one out too. And that is 1,131.3 kilojoules, okay? So the stoichiometry here is pretty easy. We're not working with grams yet, but we will at some point, and with a limiting reactant and all that kind of fun stuff. So anyway, hope this helps with thermochemical equations and stoichiometry.